Okay, I'm just going to record this again, and then I'll go back and record the other part that I missed on my own. Okay, so Dave's question was on the force location problem in 2D, the free body diagram is shown, the body is shown, the force direction is shown with an arrow, the magnitude and the angle, and then the perpendicular distance is shown. So the question was, why on the 3D problems that I did, why did I not show one moment and one force and its direction? And the reason why is it's kind of confusing. I think it's easier to show a positive, the moment around each axis, whether it's positive and negative, and show the force around each axis, on each axis rather. Let me say that again. I think it's easier to draw showing the moment around each axis and showing the force on the axis. So it's easier than drawing the moment in 3D with the three direction angles. I think that's enough to cover that answer. David, another question about that?
Yeah, I mean, maybe it's an office hours question, but I guess I'm just.
Yeah, let's do it in office hours, okay?
That's fine. Yeah.
Because I want to do what we plan to do. Okay, did I just hide? Oh, here's the textbook. Okay, so now what I want to do is let's look at the homework problems. And the first, I made two sets of homeworks, one 2D and one 3D. And I'm hoping you do 2D first, because 2D is always a little bit easier. So I'm on page 132, and we're just going to look at each question quickly to see what kind of problem it is. So the first problem is 384. Could everybody see that? Or you could look at it yourself, and I'm going to just read it. Here's the picture. Here's the schematic, 2D. A 30-pound vertical force P is applied at A to the bracket shown, which is held by a screw at B and C. A, I only asked you to do A. Replace P with an equivalent force couple system at B. So, David LR?
Yeah.
Okay, what kind of problem is this? Is it a force location problem or a force moment problem?
The force moment problem?
Great. Everybody's comfortable with that, right? Force moment. It asks for force couple. And where would you draw the force at a location, the resultant force, and you draw it at the point, and you put the moment at that point as well. Okay, next problem, 89. So now we're on Edgar. Edgar, 89. 3 control rod, let's look at the picture first. It's a rod here. It has a rod and there's some other pieces off it. 3 control rods attached to lever ABC. On its, sorry, let me say again. 3 control rods attached to a lever exert. 3 control rods attached to a lever exert on it the forces shown. I see. 3 control rods attached to a lever exert on the lever the forces shown. Replace the 3 forces with an equivalent force couple system at B. That's A. So, Eric, force couple, is it a force moment system problem or a force location problem? I know Eric's here. You're muted still. Okay, Gerardo? Hyoji?
Yes.
Okay, so it says replace the 3 forces with an equivalent force couple system. What kind of problem is that? Force moment or force location? She's muted again. Isaac?
Force couple is their way of saying force.
Great. Okay, next question. Isaac, stay with us. Determine the single force that's equivalent to the force couple system obtained in part A and specify its point of location on the lever. What is it?
That would be force location.
Okay, Jack, you're here. Next problem. Actually, let's just go through them even if they're 3D. Next problem. or another problem is this picture right here. It says replace the 150 Newton force with an equivalent force couple system at A. Jack, what is it? What kind of problem?
I believe force couple in their terminology is the force moment.
Right, great, thank you. Next problem, we have a truss here. Jason Lee?
Yes.
Okay, Jason, 113, a truss supports the loading shown. Determine the equivalent force acting on the truss and the point of interaction of its line of action perpendicular from A. What is it?
It's going to be force location problem.
Okay, I think we could stop. I think you're getting the picture. You know what kind of problems they are. So let's start working on the problems now. You all have a textbook or it online, I'm hoping. So let me go back to the webcam. So now this is your class. You determine what you want. Do you want to work on the problems all together, or do you want to have breakout rooms? What do you want to do?
How
Could
many?
we do the first
Be
one,
down
like the
for
first two
breakout.
together, and then do breakout rooms?
Yeah, that's
Okay.
what I was thinking.
Okay, so let's start with the first one together. It's on page 80, on page 132.
So it's 84A, 89, and 113.
Hang on. No, I just went over some of them. Oh, the 2D? Yeah, 84A, 89, and 113, correct.
And
Yeah.
that's just the
There are
2D
three-
ones, and
there are
we'll have
only
3D
two-
ones as
three-
well.
There are only 3 2D ones, correct.
Gotcha. And are these already up on Canvas as a homework?
Yeah, they are.
Okay,
I didn't
I guess
post
I
the
just missed it.
solutions yet. Hey, there are some of you that are telling me you'd rather do breakout rooms. Do you guys want to move into breakout rooms? Those of you who want to go into breakout rooms, do you want to move into breakout rooms now? I'm not hearing anything or seeing anything in the chat. All right, let's do the first one together. Okay, the first one's 84. So here's the sketch. So we have a bracket here. We have a force P that's out at 5 inches. And there's a screw at point B and C. It says that that P is 30 pounds. So it's a 30-pound vertical force is applied at A to a bracket shown, which is held by screws A and B. Replace P with an equivalent force couple system at B. So what's the first step? We're up to Jordan. What's the first step on both these kind of problems?
Look for couples.
Great. Good. So that was the first step always from now on. And I didn't even write it down in that directions. Yeah. Any couples, Jordan? Good job.
No.
Okay. So then what's the first step for equivalent systems problems?
Pass.
Okay. Cody? Laura? Yeah, Laura's not here, I don't think. Liam? Luis?
You skipped
Oh,
me.
Jason, I skipped you. Okay, you're next. Okay, Luis?
Yeah, John.
Okay, Luis, what's the first step we do in these force moment and force location?
I'm gonna pass on this one.
Okay, Jason.
Uh-oh. Well, so luckily it's already orthogonal for us, so we don't need to resolve it into components because I mean, that would be the next step, but it's already essentially done. So I think what we can do is set up we can set up, I think we could actually go straight into determining the moment about any point.
Okay, so I want to go back to the overview where it had the steps, okay? Because we should be able to memorize it. I know I don't like memorizing. I'm not good at memorizing, but this one's got to be easy. What's the first step? Find the resultant force. First step of both of them. Then find the resultant moment at the point in question. And then the only thing different between the force location is then you have to find the perpendicular distance. And then lastly, for both of them, you have to draw it. Okay, first step, resultant force. Second step, resultant moment. If it's a force location problem, you divide the moment by the force to get the perpendicular distance. And then the last step is to draw the body with the whether it's the force at a distance or force at a moment. So now I'm going to stop sharing and we're going to go back. Okay, so the first step for these problems is to find the resultant force. Luis, I'm going to go back to you. What's the resultant force of this system?
John, I'm gonna pass again.
No, you shouldn't.
I'm trying to pull up the book and then.
Okay, so, okay, look at my picture. Look at my
Okay.
picture. Okay, this is the picture. They told you that P is 30 pounds. And that's the only force on the system. What's the resultant force on the system? Tell me it in vector form.
Joanne, I'm gonna pass.
Okay.
I'm not paying attention right now.
Okay, no problem. Okay, Mackenzie? You're on mute? Okay, Marcine.
Assuming, oh yeah, you drew the axes, so that's PJ.
PJ, right? And since we know it's 30 pounds, well, let's give it a value.
30 pounds PJ?
No P, right? Anymore?
Yeah.
So the resultant force is equal to negative 30 J pounds. Does everybody agree? So my notations, I'm putting FR, resultant force, and I'm putting MR, resultant moment. Okay. So the resultant force is negative 30 J pounds. Okay, Maria, you're next. What's the resultant moment on this? What point are we concerned about? It's point B. What's the moment about point B? Right hand roll.
It's going to be the perpendicular distance. So it's going to be 5 inches or 2 inches.
So here's the force, right? Can you see the force? We're trying to find the moment about point B, and this is the line of action of the force, right? It's going down.
Okay.
So what's,
it's gonna be 5
what?
inches. It's going to be 5
Right.
times 30, and then it's going to be positive.
Great. And what direction is it in?
The Z direction, positive Z.
Correct. So it's positive 30 pounds times 5. And so it's positive 150, and it's in the K direction, and the units are inch pound. So we found the resultant force, we found the resultant moment. And because this is a force moment system, Matthew, what's our next step? We found the resultant force, we found the resultant moment. What's the next step?
Our next step would be to draw a free body diagram.
Great. And you draw the whole part. So you have to draw the whole part. You have to draw A, B, and C. And you have to put all the dimensions on it. Let me write that in the notes just so that you remember. Okay. So did everybody draw the bracket already?
So I'm a little bit lost. I got lost when we were finding the resultant force.
Okay. I think you guys are maybe thinking it's more overthinking it, that it's more complicated than it is.
That is extremely likely.
Okay. All
That's
right.
my forte.
So let's start. Is everybody, some of you got it, so you could just keep drawing. Okay, we look at this problem. There's only one force in here. So the only force in the system is this 30-pound force going down. And let's write it in vector form. So negative 30 J pounds.
So that's our resultant force. That's the whole
That's our
thing.
resultant force.
Gotcha.
So basically this body, because of this force, let me keep going. Then we wanted to find the resultant moment. Well, there's only one force. So we're trying to find the resultant moment about point B. And I forgot to put B on there. I should have.
Objection.
So, what?
How could there be a moment if there's only one force?
Because
it's at a perpendicular distance from a point.
Because this force is trying to create a moment about point B.
Not if there's not a force at B.
Say that again, please.
There's a force at B.
There is no force at B on this body yet. Let me just finish it, Jason, okay? Okay. So just hang with me. So there's one force here. So in order to, I have to find the moment about B. So it's going to be P times 5, and it's a positive moment. So here, Jason, here's what you want to hear. This force P, everybody, you got to listen to me now. Stop your drawing. This force P is trying to take this bracket and push it down 30 pounds. And this force P is also trying to spin this bracket to 150 inch-pounds in the positive direction about B. So this force is trying to push the bracket down, and it's trying to spin the bracket. But why is it not doing that, Jason?
Because it's bolted to the wall? What do you mean?
Because it's bolted to the wall. It's screwed, actually. Isn't it screws?
Yeah, screws.
It's screwed to the wall. So what does that mean in terms of engineering? Well, now that we know it's trying to knock the wall down 30 pounds, knock the bracket down 30 pounds, and it's trying to spin the bracket 150 inch-pound, we have to choose 2 screws that are going to be able to withstand both of those. Right? So 30 pounds. Can you think of 30 pounds?
Yeah.
When I was a kid, I used to work at an ice cream parlor, and the sprinkle box was 25 pounds. And I still have a good memory of what 25 pounds feels like. So you guys get some memory. If I had a 30-pound picture frame and I wanted to stick it in the wall, a small nail is not going to cut it. Let's say the nail is really bolted to the wall really well. Well, that small nail probably doesn't have a shear strength of 30 pounds. Let's assume you picked one that doesn't have a shear strength. Shear is when you have something, I'm looking at this, and shear is when it breaks, right here. The piece is shear. So we have to, as engineers, design these bolts so that it's that it can withstand 30-pound shear and 150-pound moment, inch-pound moment. Okay? We are not looking at connections yet, Jason, because right now we're still, the statics textbook author and I still want to make sure that you know how to calculate moments. So until we get to the end of the chapter, then I will assume you know moments, and then we go on to figuring out connections. In fact, tomorrow you're starting to look at connections.
What
Got
would a
it?
free body diagram of this look like?
So a free body diagram, well, we're not drawing. we are drawing what I am asking you to draw. And whether you want to call it a free body diagram or not, you can. Well, maybe you shouldn't, because we're not drawing in the forces due to the screws yet. So I am drawing a free body diagram. What did it ask in the overview? Draw a free body diagram of the body with the dimensions, with the axes, and I am showing the force. If you could see the green, I am showing the force and the moment, the force moment at point B. So the third step is to draw the body with the axes and the dimensions and draw the force and the moment at that point. So the picture that is given, 30 pounds away from B causes the same, is trying to cause the same linear and rotational motion as my equivalent moment, force moment drawing here. Thumbs up. You have to draw a free body diagram of the whole body with the axes and the distances.
Why do you have an arrow going from the level where A is down to B? I'm a little lost on that.
The only arrow I have drawn here, I have two arrows drawn. One is for the force.
Yeah, that's the one I'm talking about.
Well, there's a force. It's a force moment system, right?
Mhm.
And this arrow. So what I'm doing, who is that asking that?
Tony?
Tony. Okay, Tony. This P force is trying to push this bracket down. If I only draw the moment here and I don't draw the force, this bracket is only being caused to spin. This bracket is being pushed down 30 pounds and spun 150 inch-pounds at this point.
Okay. I think I was just a little confused because I saw it being applied at the end at point A.
Oh, it's right here. Oh, it was at A.
Mm-hmm.
Here it was at A, but it was creating a moment about B. If I move this vertical force to B, there's no moment at B unless I draw a concentrated moment at B.
Okay. Thank you.
So let's look back. Everybody with me? I have this bracket. I have this bracket screwed to the wall. I take a hammer, I take a hammer and I bang it at point A, 30 pounds. That is the same as banging the hammer 30 pounds here and putting a screwdriver in of 150 inch-pound at the same point. Banging it with the hammer 5 inches out is creating a moment about here. It's trying to pull the screw out. If I bang it and unscrew it at the same time, it's the same effect. Applying a moment, I'm not unscrewing it this direction. Okay?
Joanne, so basically for this problem, when it asks us like, okay, find the equivalent system, it's basically saying like draw the resultant of the whole system at this point.
Exactly.
So that picture is our answer basically.
Yes.
Because the numbers are the same.
Right.
Okay.
Yeah. So you are trying to find a result. Say it again, because you said it really well.
Draw the resultant.
No, before that. You said this problem is trying to.
This problem is trying, I don't remember.
Okay. This problem is trying to find the resultant motion, possible motion on this bracket. It's called an equivalent. Either isn't, in a way, you guys, isn't this like a force location problem? There's a force at a distance that's creating the same force and moment as this. This is a force moment here. This is really given because it's only one force. This is a force location. Dave?
Yeah, I think I think what Jason's question is that those things seem different. He's saying like pushing out at A is different than pushing down at B. But the way Maria said it helped me clarify it. It's that pushing down at A is equivalent to pushing and twisting at B.
Correct. Pushing at A is equivalent to pushing and twisting at B. Because point B is the point in question. What is point B experiencing with this 30-pound force? If it was a free body, this whole bracket would start moving down due to that 30 pounds, and it would also twist due to that 30 pounds. What, Jason?
Jason still doesn't like it. Okay.
Okay, you know, you're not gonna railroad me. That's a good word. Don't railroad everyone right now with your intellectual capacity. I'm gonna keep you quiet. Uh-oh, Jordan has these big eyes on our face. Jason, I'm not I am not condemning you. I am applauding you. This is all applaud with a New York way. But I don't want to spend the time talking to you. We'll spend it outside of class. Let's keep going. Are you okay? Give me a thumbs up that you're feeling okay.
Feeling great.
Okay, thank you. All right, let's go to the next problem. I mean, the discussions that Jason wants to have are so valuable, but if we just do that, then we can't solve a lot of problems, you know? So, okay, maybe I should have these video recordings of Jason and I outside of class and post them to Canvas so that you could get that other depth. Jordan's shaking her head, yes. Okay, let's go. 89. Myra?
So that was the whole problem.
That was it.
Gotcha.
See, I mean, it's not as complicated as you think. Here's a force at a distance. I want to know what an equivalent system is with the force and the moment at the point in question. Those two are exactly the same. Okay, next, look at 89 now. Now we have three forces on a system. I'm up to Myra.
Yeah.
Okay, Myra. A says replace the three forces with an equivalent force couple system. Is A a force moment or a force location problem?
Force moment.
Force moment problem. So what's the first step, Myra? What's the first step of a force moment? Or actually, what's the first step of either one?
Finding the resultant force.
That's correct. Finding the resultant force. Okay. So, but before you do that, let's look at the problem a little bit more.
Step 0, look for couples.
Good. Look for couples. Are there any couples here? Where are we? Miles. Nope. Peter? Are there any couples here?
I'm not seeing any.
Okay, look close. It's this picture. Let me zoom in. Okay. Do you see any couples?
Oh, there's a couple of from B to C.
Wait. Couples, remember, are two forces, same magnitude, opposite in direction. Look closer. I'm looking at 89. I don't know.
Right.
If
A and C, you have a 20-pound.
Right. Right. You guys, this is awesome. There's a 20-pound couple here. What's the resultant? Tim here? Tony. What is the resultant force due to the 20-pound couple?
Resultant force.
Force.
Dang.
Okay. This 20 is going to the left. This 20 is going to the right. They are
zero?
couples. Zero. The resultant force due to the 20 is 0.
Okay.
What's the resultant force of the 48? What do we have to do? Victoria, in order to find this resultant of the 48, what do I need to do? How do we represent resultant forces? It's a vector, right?
Yes. So you would do 45.
Don't do the math for me. Just tell me what I need to do.
I don't know, I pass.
Okay. Amani,
Break into components.
break it into components because the way we represent forces are it's a vector. Put it in vector form. Okay, now don't go and do the math yet, everyone. Look, we want to simplify it a little bit more. Normally we have our axis. Normally we have our XY axis like, regular. But would there be a better direction to put your XY axis on this problem? In fact, on the moment quiz, Isaac rotated his axis and put it in a way that would simplify the problem. So think about, and Amani, you want to do it? How would you put the axis?
I would just put it along the,
Excellent.
whatever that is called.
Put the axis like this. And Amani, why does this simplify the problem? Can you think about that? Oh, let me just read the question again. Replace the three forces with an equivalent force moment couple system at B. So let me circle B. In the end, we're going to have to find the resultant force and resultant moment about B. Why is putting the axis like this better or quicker?
It would help with the angles.
Okay, certainly we have the angle, so it would help. The 55 we could use, so that's one reason that it helps, but why else?
And it's also the same as point B.
Right, the X component of the force would be along the line of bracket ABC and would go through B. So would the X component of this force create a moment about B?
No.
Would the Y component create a moment about B?
Yes.
Okay, so you guys, before rushing into this problem, we just spent 3 minutes, maybe 5 minutes. But you may have we did it 5 minutes because it's, there's 25 of us. But if you did it yourself, it would have taken you 2 minutes to realize there's a couple that creates no that creates no resultant force. And you could find the moment quickly from the couple. And then to decide that you want, because remember, a couple creates a moment, the same moment all over the system. So this couple creates the same moment as at A, at B, and at C. And then you guys decided to rotate the X and Y axis so that one of the component, the X component of 48, doesn't create a moment about B. So now go ahead and find the resultant force and the resultant moment at point B.
Joanne, quick
Yeah.
question. What is the number of this problem?
89. Sorry, Angel. Is it really hard to see it on the screen? You guys, yeah.
The quality is kind of grainy.
Yeah.
But we can make out what's going on.
What if I remove the light? Is that any better? Because maybe it's the reflection.
I think it's just the camera resolution. It's just the
Alright.
kind of camera you're using, unfortunately.
Alright. Okay. Okay, if you want to check your answers or check my answers. The resultant force I got was 39.3 I plus 27.5 J. Did somebody else get that? Okay. And then the resultant moment was a negative 491 in the negative Z direction. Did somebody get that?
I actually got 36.9 for the for the J component of the force. I'm not sure if I used the
Okay,
right.
somebody gave me a thumbs up, so I think mine's correct.
Oh
And
wait, I just
actually,
realized I used the wrong force.
Yeah.
I used 45 instead of 48.
Okay, so you guys, you probably have determined by now in statics, it's very easy to make a mistake. It's very easy to make a mistake. And that's why I want you to follow the steps so I know exactly what you did. And when you make a little mistake, I'm not going to take off a lot. But if you don't show me what you're doing and I don't know what you're doing, and you get the wrong answer, you're screwed because I have no idea how you got the wrong answer. Dave, were you going to say something?
I had a small, I guess I also had a small error. I think what I missed was I used 20 for the couple moment, but you needed to find the vertical component of the couple. Is that right?
Yes. Yes. Take a look at this. This is another reason I changed the axes, you guys. Everybody, this is really important. Look at this. Another thing we should have talked about. When I break this couple, if I wanted to, I mean, basically I need to get the perpendicular distance here, right? In order to take the 20, is everybody watching me? In order to find the moment created by the 20 pound couple, here's the 20, here's the 20, I'd have to find the perpendicular distance between. And I probably could find it with geometry. But instead what I did is I just broke it up. Instead, I broke it up into a Y component and an X component, and then the X components go through each other. They cancel each other out, and they go through B. They don't create a moment, so I only did the Y component. In the end, the math is the same. Either you take the 20 and you multiply by the perpendicular distance, or you take the Y component of the 20 and multiply it by the perpendicular distance. So this is the deal. You could either take the 20 and calculate the perpendicular distance. Instead, what I did is I calculated the Y component and then I put in the 70. In either way, the math's going to come out the same.
Joanne, I have a question.
Yeah,
Can
hang
I
on,
look at
Angel.
your? Yeah, for sure.
Angel, hang on a second.
Yeah, I don't quite follow that. I think that the distance between A and C is still 70. So if you had them off at angles like that, it would still be 70, right?
No, you can't, David, because the rule with couples is you multiply the couple force by the perpendicular distance. And the perpendicular distance is this distance right here, this leg of
I got it. That drawing
triangle.
helped. That drawing helped. Thank you.
Okay, great. Everybody see that?
So if we're using only the Y component, we multiply by.
If you're using the Y component, then you could use the 70.
Gotcha.
It's the same math though, right? If this right here is 30 degrees, let's see, that's not 30. Let's see the math. Let's see, this is 20.
70.
70, thank you. Basically what I need to do is I need to get this distance right here, right? Do it both ways. You know this stuff. This is trigonometry. You know this stuff. I'm going to erase my.
What answer did you get?
Negative 491. Did somebody get that?
I got 489.6. I got
Right.
negative 489.6. It's close.
Right, that's fine. We're gonna start getting more rounding errors now, because now we're multiplying a distance by a force. So I got negative 491. Somebody got what, negative 480 something?
Joanne?
489.6.
Yeah.
Yeah.
Hang on, Maria. I still got to go with Angel. The reason why is there's rounding, right? So it depends on how many decimal places your calculator carries out. Okay. Angel, did you get your question answered already?
No, I think,
Okay, so what's your question?
can I look at the force components you got, your resultant force?
Yeah. Do you want to see the math?
Yeah, and just the results.
All right, hang on.
I think.
I mean, you know, I'll post this so you'll have it, but I don't think we should go back to finding errors in components.
Okay.
Right? Because we should know already, and you're gonna, you know, just trying, but I'll post what F1, F2, I'll post it all. Okay.
All right.
Okay, Maria. The point is you need to know how to do these newish problems. Maria?
Okay, so I have a question. For the moment caused by the couples, it's gonna be the same at any point in the system, that I know, but do I have to add the moment from both? Because it's just in reference to the other couple, right? So it would be just 1 times the cosine of 20 times the force in the y direction.
Correct. Take Maria, look up here. I'm trying to find the moment about point B, right?
Uh-huh.
We know the couple creates the same moment about every single point. So you take the 20 pounds, cosine of 20, multiply it by the perpendicular distance, and that 20-pound moment you just calculated. And it's the same at every point. So that means that at B, whatever that moment is, you got it. Then you have to take the y component of 48 and multiply it by 30, and it's a positive. So the moment about B is the moment that you calculated due to the couple, plus the moment about the y component of 48 times 30.
But if you get the y component for one side of the couple, then you take the perpendicular distance to the other couple, it's not really the perpendicular distance, is it?
Gotcha. Okay, so we took this couple. I see what your question is now. We took this couple and we made a y component of the couple, right?
Uh-huh.
And then we had an x component of the couple. Is there a distance between, is there a perpendicular distance between the x component of the couple?
No.
They go right through each other. So I understand what your question is now. Yes, if we have a couple and we break the couple into components, we have to find the moment due to the y couple and the x couple. It just happens in this problem that the x couple, they're both of these couple forces are coming off the same line. So the x component of this force and the x component of this force go through each other, and they don't create a moment.
Okay, I get that, but my question was really like, I was just having trouble visualizing if we're only doing it to one side, like, I don't understand how you're only using one side to calculate the perpendicular distance from.
Hang on a second.
Maria, I'm curious what your question. Can you say your question again?
I'm curious, like, I think I'm just overthinking it, but it seems weird to me to be like only calculating from one side the perpendicular distance. Like if you take the y component of A, of the force at A, and then you find the perpendicular.
Oh, I got you. We're finding the perpendicular distance between them. When you do it, when you calculate a couple, it's the distance between the two arms of the couple.
But it's between the two y arms of the couple?
Well, what we did is we rotated our axes. so that we can eliminate the X components entirely. So if we
Yeah,
hadn't,
that
yeah,
I understand. That I understand. But like when we're taking the perpendicular distance, then it is just between the two y components of the.
Okay, ready? Ready,
it's a good
Maria?
question.
Okay, let me go.
Would-
Can I do it?
Yeah.
Okay, you're okay with the 48 pound, right?
Yeah.
Okay, so we have this couple here and,
I can't see. You gotta move it
oh,
up.
oh, right. Okay, so we have this couple that's going here and it's 20 and here and it's 20.
Uh-huh.
I don't want to try to find this perpendicular distance between them. Okay, you're good with that, right?
Yeah.
Okay. So instead, what I'm doing is I'm breaking this couple up into a 20y and a 20y and a 20, an x component of the 20 and an x component of the 20. Now I'm comfortable. The problem might be is that you didn't do the couple homework yet, right? It wasn't due yet, right?
No.
Okay, so here's the perpendicular distance between those two, which is the 70. The x value goes right, these two go through each other, so there is no perpendicular distance. Had the 20 been over here and the 20 been over here, then I would have found what the perpendicular distance is. Maria,
Uh-huh.
still?
Yeah, I mean I get it. Like I get it, but I just
What is it that, tell me what's confusing. Can I erase it and tell me what's confusing?
I don't know what's confusing. I don't know how to put it into words.
Okay.
But I mean I get it. I just like I don't know how to describe it.
Okay,
It's not
I'm gonna keep going then, okay?
Yes, that's fine.
All right. So we found, this was a force moment problem, right? So we found the resultant force, we found the resultant moment, and then we have to draw the bracket. Here's the bracket. I probably should draw the other parts of it. I don't know. I think drawing just bracket A to C is fine. So I drew the bracket going A to C, and then at B, I put the resultant force and I put the moment. Okay, I need to go on because I want to do force location problems. B part of this, it says determine the single force that's equivalent to the force couple system obtained in part A and specify its point of action, right? And we're looking for the perpendicular distance. So remember, for a force location problem, first step, find the resultant force, which we already found, it's 48 pounds. Find the resultant moment, which is a negative 491 inch-pound. Third step, find the perpendicular distance. And the perpendicular distance is 491 divided by 48, and it comes out to be 10.2. So we found the resultant force, we found the resultant moment, we solved for the perpendicular distance, and the last step is to draw it. So now I drew it, drew the bracket again, A, B, C. I knew the force was going off at a 35-degree angle, and I wanted to I found the perpendicular distance that force has to be out to create the moment about B. So my question is, why is the force, and I don't know where we are. Edgar?
Yes.
Why did I draw this resultant force of 48 inches to the left of B and not to the right of B? Why didn't I draw it where my pencil is?
Because I was gonna give you a different direction for the moment.
Great. We got a resultant moment of negative. We know the force is going up to the right. The force is going up to the right. In order for a force going up to the right to create a negative moment, it had to be drawn to the left of point B.
So did we ignore rotating the axes as far as the resultant force is concerned? We just did that to make the moment convenient?
No, we could still have the axis here. This could still be X, and this could still be Y, right? This could still be X and Y.
Yeah.
Regardless of how I put my axis, the force is still in the same direction. The force is still off 55 degrees or 35 degrees here.
We're not representing it in vector form. We're just saying 48 pounds in
Yeah, we're just putting,
so-and-so
we're
direction.
drawing it. We're just drawing
Oh,
it.
okay. Okay. Cool.
48 pounds at an angle. Maybe I drew the angle wrong here, huh? I'm looking at it now. Hang on. Yeah, I did. I drew it wrong. Boy, we're not hearing a peep out of Jason now.
I'm sitting on my hands.
I didn't really draw it that
35 degrees from X.
well. Yeah, from X. I think I need to rescan the homework. The angle is 35 degrees here. I think we should do a 3D problem now. Okay, what's stumping you guys? I have to tell you, and I don't know if I started the video with this, this is the hardest thing we do in statics, finding equivalent systems. This is the hardest thing. Well, I should say moment of inertia is hard too, but this is harder. Those are the two hardest things in statics. All right, so if you're following along, you're doing really well.
John, I have a quick review question.
Yeah.
Can you show us what we wrote down for the answer to 89A? I just want to make sure I compared those two answers.
Yeah.
A had the force at B, right? And then part B has the force away from point B.
So 89A, the answer is, what is the resultant force? What is the resultant moment? And then the sketch. But I have to find the sketch.
It wouldn't be.
Here's the sketch.
Okay, yeah. So it's still 48. It's just the whole force, and it's at that angle, and we just write in that moment we found. Okay.
That's right. You're writing in, you're putting in the resultant force and the resultant moment at a point.
Okay, I got it. And then the
So on a force
B,
moment system, you're telling me what the resultant force is, you're telling me what the resultant moment is, and then you're drawing the structure showing the resultant force and the resultant moment at the point. For a force location problem, you're calculating, again, you have the resultant force, you have the resultant moment, you're calculating the perpendicular distance, and you're drawing a picture showing the resultant force at the perpendicular distance. And I have to do a better picture.
and we knew that 35 from the sketch, from the problem sketch, right? We knew that
That's
from
correct.
the given information.
That's right.
Okay, thank you.
And, well, I should say, yes, Dave, we knew it from the beginning because it was given, but it just happened that the 48 pounds was the resultant force. If there were a bunch of forces on here, I would have to find the angle.
Right,
Of
we could
that
solve
resultant
for it. We could
force.
compute the
Direction angle.
direction angles. I got it.
Correct. So the third problem, which is 113, is like that, and you'll see. I'll post the solutions. Okay.
That helped. Thank you. I just wanted to
Okay.
distinguish the two.
Okay. Okay, so let's go to a 3D problem. Um, I think I'm just going to go over the last three problems because we don't have much time. So the first problem is 95. And let's just talk about how we would approach the problem. You guys, this is 95. This is the problem. We have one force at point D. The problem says replace the 150 Newton force with an equivalent force moment system at A. So, Isaac, force moment problem or force distance problem?
Replace the, can you read it again?
Replace the force with an equivalent force couple system at A.
Force moment.
Force moment problem. What's the resultant force? The first step is to find the resultant force, right? There's only one force there, so it's that guy.
Yeah, there's only.
Okay,
yeah.
Find it in vector form, right? They want to know basically what is the equivalent system on point A. So I solve for the resultant force. Then what do? I solve for Isaac, solve for the resultant.
And then you solve for the resultant moment.
At A. And then Amani, what's the last thing I would do? I found the resultant force. I found the resultant moment of this force on point A. And the last thing I do is?
Did you say my name?
Yes.
Yeah, we need to draw it.
Then you draw this bracket and you draw the force and the moment at A. I'm going to keep going. Next problem. This problem is very similar to the one I did in class over the video. Bon, it says that there are three kids standing on a wooden raft. They give us the weight of all of them. And it says, determine the magnitude and the point of application of the resultant of the three weights. So is this a force moment or a force location problem?
Force location.
Correct. So what's the first thing I have to do? Find
the resultant force.
Find the resultant force, which in the end is going to be what?
You would have to add up the weights of all
right,
three.
All their three weights going down.
Right.
And now I have to find the resultant moment, right? In both these problems. So you, let's see, Myra. Do these weights, do these kids create a moment about the y-axis?
No, because they're parallel.
Correct. Do they create a moment about the z?
Yes.
Keep going, Myra. Yes, positive or negative?
It would be negative.
Fingers in the direction of the force, palm towards z. Did you get positive or negative?
Negative.
Great. And how about x? Do they create a moment about the x?
A positive one.
A positive moment about the x. So this is a force location problem. First thing, find the resultant force. Next thing, find the resultant moment. We know that these guys do not create a spin about the y-axis, but they do create a spin about the z and the x. So find the moments about x and z. Then, since it's a force location problem, we have to find out where that force is on this raft to be equivalent to these three kids standing where they're standing. based on the moments that it creates on the axes. It's a complicated problem. You might want to watch the video again for this one. There's a parallel force problem. Okay, third and last problem that's 3D. Mackenzie? Jack? Jack, you there?
Yeah, I'm here.
Okay, so this problem says 4 signs are mounted on the frame spanning a highway. The magnitude of the horizontal wind forces acting on the signs are shown. So this 105, 160, 90, and 50 are all represent wind forces on here. Determine the magnitude and the point of application of the resultant of the 4 wind forces, and then they give you what A and B are. So, force location or force moment problem?
Force location.
Force location problem. So do these forces create a moment on, do you see where the axes are? This says X. This says Y. This says X and this says Y. So Z is here, I drew it. Do they create a moment about the Z?
No,
No, but they create a moment about the Y and the X.
that's correct.
Do they create a positive or negative moment about the Y?
Positive.
Correct. Fingers go in the direction of the force, palm goes towards the Y-axis. How about Jack about the X-axis? How about, sorry, let me separate them. F, G, and H. F, G, and H, all those forces are below this bar BC. Do they create a positive or negative moment about X?
I believe all those are positive and E is negative.
Right, because E is above bar BC, so it creates a negative moment.
I think I disagree.
Okay, so the 90 pounds is above the bar, right? So your fingers go in direction of the 90 and palm goes towards the x-axis. The
Right.
positive x-axis is on this side and my thumb is sticking in the negative.
Oh, really? You're saying that drawing means positive is back?
Yeah.
That's
Always-
unusual. Okay, got it.
Always, right. Always look, whenever you do a 3D problem, first thing you do is you look at the way they drew the axes. The positive x-axis is here. The positive y-axis is here. And then I drew the positive z-axis here.
Okay, yeah, I don't think I've ever seen it like that, where the
Yeah.
positive goes back like that.
Right.
It's just
Think of it in terms of you're on the freeway, you're driving on a highway going underneath all these signs, and the x-axis is positive to the right and the y-axis is positive up and the z-axis is coming out at you. That's why they oriented it like this. Okay, let me, we're kind of out of time. Let me just come back for those who have to go to the next class. This is very complicated. Okay, so you need practice. What you might want to do is do the couple homework first. But I think the problem that we did today, 89, I think it was, that's the only one that has a couple in it. So don't worry about the couple homework. But the equivalent system homework's going to take you a while. Once you get it, you're going to be like, oh, okay. Because what you're doing is you're finding the resultant force on the system, the resultant moment at the point in question, and then for the force moment, you're just drawing the force and the moment at that point. And for the force location, you're finding the perpendicular distance and drawing the force at the distance. The idea is you look at it's fine. I'm trying to find like a really complicated problem. I mean, look at, well, I'm not going to show you this truss problem, but you could imagine looking at anything, even a telephone pole. There are a ton of forces on there. And it would be nice if we were able to simplify it to be just one force in one moment. And the reason why is because I really want to know on a telephone pole, if I know what the resultant force is and what the resultant moment is that it's creating, where the bottom of the telephone pole connects to the ground, then I know what kind of design I need to make on my connection. Because if the resultant force is 100 pounds, I know I need that connection on the ground to hold up that telephone pole to be able to withstand 100, what did I say, 100 pounds. And if it creates a moment of 500 foot-pounds, then I need to be able to withstand 500 foot-pounds. So to be able to reduce a whole system to one force in one moment is such a great thing. Okay. Okay, so I'm on until my meeting with Carl at 1:15. So whoever wants to stay on and talk can. So I will post the solutions to this homework. And I think you have 3 homeworks, right? Do still couples, and then I separated the 2D and the 3D equivalent systems. Okay, questions? Dave?
Yeah, sorry, I had an error. You just mentioned you had a meeting. Do you still have office hours at 1 today or no?
Yeah.
Okay.
Yeah.
Okay, I'll see you
And
then.
tomorrow too.
Okay, great. Thanks.
Yeah.
When is the
Thanks, Joanne.
equivalent?
Daniel, what'd you say?
When is the equivalent homework going to be?
It's posted. I don't remember the dates.
Okay, thank you.
Look at the posting.
The first one's due, the T is due Monday or maybe Sunday, I think Sunday. And then the 3D is due Wednesday, next Wednesday. So we got a while on that.
No, it's the 2D is due Monday.
Monday, yeah.
These due Monday. Sweet.
Hooray.
Thanks, Joanne. I gotta go.
Okay, great. Thank you.
Hey, Joanne.
Yes.
Can we look at 3.89 part
Yeah.
A again?
Yeah.
Because
Yeah, I'm gonna pull it up.
awesome. I am kind of confused about when you're taking account for point A, when you're calculating for the total resultant moment.
Well, the problem asks us to find the equivalent force couple system at B, not at A.
Right. And then I saw your solution. You calculate the y component of force A and add it with y component of force C. I thought you mentioned as a couple, the force on point A cancels the negative y component of like
Okay.
the force pointing down at C.
Okay, so the resultant force, Jason, on this problem,
Mm-hmm.
the force, resultant force, the 20 and the 20 cancel.
Right.
So the only resultant force on the system is the 48 pounds up to the right.
Yes.
That's it. So I could take the 48 and get the x component and the y component so I could represent it in vector form. You're good with that?
Right. Yes.
Okay. Okay, now for the moment is what your question is?
Yes.
Okay. For the moment of the 20, either, let me find the, here it is. I have a 20 here, and I have a 20 here. And in order
Yes.
to find the moment due to a couple, I take the magnitude of the force and I multiply it by the perpendicular distance. So this
Mhm.
perpendicular distance is the perpendicular distance right here in this triangle. But I don't want to calculate that. For me, it's easier to break the force, the couple, into components. I have a Y component and I have an X component. Do you agree?
Yes.
But now I have two couples. I have a Y couple and an X couple. And the moment due to a couple is you take the magnitude of the force. So in this case, I'm looking at this Y force, which is 20 pounds times cosine of 20. Do you agree?
Right.
So I'm taking this 20 times cosine of 20, and I'm multiplying it by the perpendicular distance between the two, which is 70.
Mhm.
And that's the couple that's created, that's going to be like this, right?
Right.
So it's going to be 20 times the cosine of 20 times the perpendicular distance of 70. That's the
Mhm.
moment that's created by the Y couple.
Okay.
The X couple, the X component of both of them, go through each other. So there's no perpendicular distance.
Mhm.
So the couple, the X couple, create no moment about the system at all because they
Mhm.
cancel each other out.
Got it.
So you have two options. Either you take the 20 pounds and you find the perpendicular distance to find that it's a negative moment in the system, or if you don't want to try to do the trig to find the distance, you break the force into X and Y components and then say there are two sets of couples, and it happens that the X couple doesn't create a moment because they cancel each other out.
Mhm.
Could I give you another example?
Yes, please.
Let's say this is 3 inches and this is 5 inches.
I can't see the whole graph.
Okay. Okay, so I have this bracket here, right? It
Yes.
goes from A, B to C.
Mhm.
And let's put the angle here. Okay, so these are both 30 pounds and they're both off at an angle. And they're off at the same angle. So I could go like this. Are they couples?
Yes.
Right, they're equal in magnitude and opposite in direction. So if I had this perpendicular distance here, let's just call it R perpendicular. The moment due to this couple is going to be 30 pounds times whatever that perpendicular distance is. And is it positive or negative, Jason Lee?
It's going to be negative.
Negative. Okay, but let's say I don't have that perpendicular distance. Instead, what I'm going to do is I'm going to break this couple. Here's the 30y, here's the 30x, and here's a 30x, and here's the 30y. there are two couples now, right?
Mm-hmm.
So the moment is going to be equal to, there's the 30x couple, and what's its perpendicular distance?
3.
3. Does it create a positive or a negative moment?
Positive.
Right. And then I have the 30y, right? And what's
Yes.
its perpendicular distance?
5.
Right. And does it create a positive or negative?
Negative.
Negative. So in this case, the two couples, this couple was at A, and this force was at A, and this force were at C, and they were at a distance apart. It was one couple, and I could have, if I knew the perpendicular distance between the line of action of both those forces,
Mm-hmm.
I could find the moment, 30 times whatever the perpendicular distance is. But if I don't want to calculate the perpendicular distance, then I could break each force into components and solve for the moment due to each couple separately. Does this
Mm-hmm.
make sense?
Yes.
Okay.
I think the most confusing part about this topic is if you're finding, if you have a couple, it means it doesn't have resultant force. But it doesn't
That's
mean
correct.
it doesn't have resultant moment.
A couple has does not have a resultant force.
Mm-hmm.
It has a resultant moment.
Yes.
Okay. So I'm going to take a bracket. Hang on. Let's find something. Okay, I have this bracket right here. Everybody looking?
Mm-hmm.
I'm applying a force here of 10 pounds, and I'm applying a force here of 10 pounds. This whole damn thing is spinning. The
Yes.
same spin. Right? But it only spun. If I did indeed perfectly put the same load in both places, it would not have moved side to side. But if I put 40 pounds here and 30 pounds here, I'm not only causing it to spin, I'm also causing the whole thing to move here. So when I apply a couple, which is like a screwdriver, if I put a screwdriver in here and spin it, this whole thing is spinning.
Mm-hmm.
A screwdriver, think of a screwdriver. Oh, we can do a top. Look at this. A top is really applying a couple because I'm putting the same force on this finger and the same force on this finger, and I'm trying to spin it. I'm putting a couple on here. Does that make sense?
Yes.
In fact, even if I grab it up at the top, I'm really putting a couple on it. It's a force in this direction, a force in that direction, and there's a distance between them. So it's a couple. So every time you put a screwdriver in, what you're really doing is you're applying a concentrated moment. Where here, I'm actually trying to put two couples. I mean, a couple period. Okay, Jason, let's hear some questions.
Yeah, I'm trying to get my head around the idea of a concentrated moment. It's
a moment at a point.
It's a moment at a point.
I think the screwdriver is the best way to describe it. You are.
I think that's a great physical analogy. So what, so if I have, so yeah, so take your bracket, you have your two forces, and then we could think of that as a concentrated moment, right? That's the equivalency.
That's right. That's right. A couple is like a concentrated moment.
Okay.
Okay, I have to go head to Carl.
Okay, thank you.
Okay, you're welcome.
Done.
Thanks, Joanne.
Okay.
Thanks, sir.
Okay, I'll see you guys.